Welcome to Zero Knowledge, a podcast where we talk about the latest in zero knowledge research and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
This week, Frederick and I chat with Omer Shlomovits from Zengo Wallet. We talk about MPC, Threshold Cryptography, and how this work is being used in a blockchain context. But before we start in, I want to say a big thank you to this week's sponsor, Least Authority. Least Authority is a team of researchers, cryptographers, open source developers, and privacy advocates. They are a security consulting company known for their dedication to pushing the limits on how to build privacy-respecting solutions. They specialize in security audits like the ETH2 specification, Protocol Labs' Gossip Sub protocol, Atomic's library wallet and smart contracts for the Tezos Foundation, Blockstack's investor wallet, Centrifuge's TinLake 3.0, and more. They wanted me to let you know that they are currently working on a step-by-step guide to building ZK snarks called the Moon Math Manual. You can find and donate to this project on Gitcoin grants. Matching round 8 is starting this week. Speaking of, the Zero Knowledge podcast also has a grant on Gitcoin, so when you head over to the site, do consider donating to both. I've added the links in the show notes. Lastly, Least Authority is also hiring. So if you're interested in working with Least Authority on anything zero knowledge related, head over to their career page to learn more about the security auditor position they have open. You can find that at leastauthority.com/careers. I've also added the link to this in the show notes. So thank you again, Least Authority. Now here is our interview with Omer. Today we're sitting with Omer Shlomovits from Zengo Wallet, and we're going to be revisiting a little bit the topic of MPCs and covering primarily the topic of threshold cryptography. So welcome to the show, Omer.
Hi, great to be here. Thank you for having me.
I think we got to know each other a little bit through a research group that you've created called Zengo X. I think what would be interesting to kick off this interview is to hear a little bit about Zengo and Zengo X. What are those two entities and how are you related to them?
Yeah, so Zengo is a company building a wallet for consumers, crypto wallet. It's a company that I co-founded, and as part of my role in the company, I had research in a research group, which we named Zengo X, which was not the original name, but this is the name we gave it now. This group exists on GitHub, which, if you think about it, is kind of a social network with the issue tracker and the PR, and you can start stuff and you can follow and so on. And we felt the need that something was missing, right? So we wrote a lot of cryptographic libraries that are very specific to require to all sorts of use cases. And we felt that people that are coming to the GitHub or to our GitHub organization are sometimes lost, and the conversion from taking them from being just a visitor to being a contributor is something that we want to improve. So what we've done in the beginning is that we've just added a link to a Telegram group, and instead of asking for contributions and so on, just told them, look, we want to know you, we want to meet you, we want to discuss, let's work together. And it was, I guess, it's a successful experiment because it organically kind of attracted very interesting people from the space and even a bit from outside the space, which have common interest to a very specific use of cryptography. So that group just grew, and obviously it's now also exists on Telegram. And what we do is that, first of all, this is like the main group is kind of like the front, but there are many side rooms that have very vivid discussions around all sorts of topics that include research. What happened is that while we started by being focused on something called threshold cryptography, we noticed that there is also room for other kind of research-related topics around cryptography to be discussed that are related to the space. I mean, the space is pushing forward the entire field of cryptography. So based on demand, we kind of shared more and more of what we are doing, which also evolved from just threshold cryptography to more cryptographic application that are heavily relying on cryptography that can be used in the blockchain space. So yeah, that's kind of how research group came to be, which is, I would say, like 50% more oriented to cryptographic code and implementation, and 50% to research. And out of this 50%, also some part of it is for general research in cryptography. And from time to time, we try to, it's one thing to bring people to come and talk and discuss. The other thing is to keep them engaged and feel comfortable to talk about all sorts of questions that they have, like engage with discussions. So we start to do all sorts of activities around this group, which includes, at some point, we had the webinars around cryptography from people from the, let's call it community or ecosystem. We also started some study groups, one about class groups, which was highly successful. I think now we have one of the, maybe the only one for specific use cases, class groups in Rust libraries. And it's there's like a cost. It's not cheap to get the knowledge about class groups, so it really was helpful. And that kind of activities. I can go on and on. But the end result is that now it's an ecosystem, and then we see it growing by the day, and gets a lot of engagement, and eventually we're also getting a lot of contributions. And this is the core of Zengo X. It's contributors working together to solve interesting research problems and also to build cool libraries in cryptography.
It feels pretty unique to have this sort of research group come out of a wallet, essentially, where like it's pretty commonplace that sort of a core team has a research group as well, or something like the Ethereum Foundation has a research group. But I've never really heard a wallet company have that. So what is your goal to like contribute that back to the wallet, or is it so like disconnected from that at this point that is really about fundamental research or even contributing research back to the protocols?
Yes, so it's a great question. Now we need to understand how Zengo started. And when it started, so my angle, I came from academia. I met my co-founder, Uriel, which was is a seasoned entrepreneur. And he came up with this issue of a wallet, which never bothered me. But after sleeping on it, I realized that this is a true pain. Now, I came with some background in MPC, and it took us some like basic research until we figured out that this is what we wanted to do. Like, we need to build key management, which is one of the cores of building a wallet in the space around multi-party computation or threshold cryptography or threshold signatures. And from that point, I spent pretty much 24/7 implementing MPC, which was in its infancy. It was very surprising to see what it was at that time. Now, as you said, when you build a product at the early stage, there's a lot of R&D, and the research was very much related at this point to what we build in the wallet. For example, I think the first real research we've done was around recovery. You need to build a recovery scheme that would be equivalent to your primary way of handling the keys, right? Because otherwise the attacker would just go to your secondary way of how you do recovery and would get the key out of this way. So we try to solve recovery, and because we are using MPC, we try to stay with the same assumptions and so on. And eventually, I think we presented it at the Stanford Blockchain Conference. And what happened is that I would guess some part of it is due to luck, is that this area, specifically threshold cryptography in relevant to blockchain space, attracted a lot of folks from academia at the same time. So there's been a huge surge of research that is focused on this area, which meant that for us, it was very easy to first, since we're kind of one of the first to actually try to work with those primitives and protocols. We encountered all sorts of problems that has some value to academia people. So it was easy to start collaborate with them. So this was the focus of the early days. But from that point, while we started to establish the research community and like answering those questions, it opened up to broader questions. For example, so how do you do MPC when you have a lot of parties, right? Not just 2 or 3, which was the common case. What happened when you have 1,000 parties? So it kind of led us to this fundamental question that eventually, for example, in this question, we wanted to answer on how do you build a communication layer in the right way for MPC? For example, based on some state machine replication, BFT, this was like our angle. So yeah, it diverged and that point. Now, what we have now is that our research is probably ahead of the product. And it's also, by the way, after you launch, it's harder to change cryptography. But the research is still supporting most of what we do in the cryptographic layer in the product and in security stack. And it also supports other products of other companies that are using the code. Everything is open source. So there is this ecosystem and there are questions around it. And we also allow us for all the time to seek for alternatives to try and improve. After you solve something about security, you want to improve the efficiency. So this is like another line of research. So I would say that there is a lot of connection between our origin and what we are doing now, but there is yet another big chunk of research that is not directly affecting the product in the near future.
What you describe as this community building sounds a lot like the Zero Knowledge Podcast Telegram group and then the ZK Study Club and some of the projects that we've been building, obviously a bit more focused on the zero knowledge specific space, but there's so much overlap I find with your group. And I know when I first joined it and got to see what was happening in there, it just seemed like it would be inevitable that eventually we'd have a conversation and hopefully get to share some of that info.
Yeah. No, the study clubs are really successful. I think probably what inspired me to do our study groups, although they kind of picked up a different approach, but I think it was the inspiration. Yeah, we get a lot of inspiration from the zero knowledge ecosystem.
Oh, cool. So we've heard the story from the founding of the company onwards, but can you tell us a little bit about what happened before that led you here?
The story is kind of simple. Around the launch of Ethereum, I think this is where I picked it up. Smart contracts kind of blew my mind. So I read the yellow paper much before I read the Bitcoin paper, the white paper. My first attempt was to find an issue with the Ethereum proof of work, the ETH-hash. It was actually an existing algorithm that Vitalik kind of tweaked. And my goal was I knew that there was no security proof to the tweak that Vitalik done. And I thought, and at the same time, there was a lot of other research going on about all sorts of, it's called moderate hard functions in relation to space and also memory consumption and computation. So I had a quite nice, I think, few observations. I made presentation, but nothing that I could actually make substantial contribution out of it. And I guess that from that point, I decided to not bet against Vitalik. And then eventually I met Uriel. So this is what I mentioned before.
So we had Nigel Smart from Unbound Tech and some university. Leuven, yeah. KU Leuven. It's supposed to be a cool place. We had him on a different episode to talk about MPCs and a bit of threshold cryptography. But I know you listened to that episode as well, Omer, and I think we can flesh out our knowledge of threshold crypto a little bit more. But I'm not sure that we have sort of the basics. I think we have the basics of MPC, of how you can go from a polynomial to where different parties have the different components, and we explain those kinds of things. But going into more like real world cryptography, ECDSA and the like, I don't think we really have the fundamentals there. So maybe you can help us get up to speed a little bit on that and talk about some of your own work there as well.
Sure. Starting with MPC, stands for multi-party computation. So basically what it means is what we know today is that we can take any function and we can compute it with MPC techniques, meaning that you have private inputs that you don't want to share, but you want to learn some output. So Nigel mentioned the millionaire's problem. You want to learn, for example, so the inputs would be some secret salaries, and you want to learn who is the richest party. Now, threshold cryptography, you could say that this is kind of a branch inside MPC that focuses on functions that are cryptographic. Right, so all of the cryptographic functions we know, like key generation and signing digital signatures and encryption, they all have a threshold equivalent. And you call it threshold because you need to make this threshold assumption that is parameterized by, there's two parameters, let's call them T and N. This is a common naming for them, convention. So what you want to say is that you have N parties joining the computation. And out of the N parties, you assume that no more than T are malicious, meaning that they try to sabotage the protocol and learn something about the other party's input. Okay. So why is this interesting? So for example, signatures, which is the biggest use case in the blockchain space, this is something we do all the time when we propagate a blockchain, right? When you sign a transaction, you actually do a digital signature over the transaction to sort of say that this is your identity, right? The signature is equivalent to say that I have this cryptographically proven identity that I'm attaching to the transaction. Why is this interesting in terms of cryptography? So let's take, for example, digital signatures. So in blockchain, this is what we do for every transaction. We attach a signature, which is basically like saying I have a cryptographic proof that this transaction came from me. Like I'm saying this is my identity, and no one can forge it. Right? The basic security property of signature is that it can be unforgeable. However, it is some kind of a single point of failure for once. So one motivation for using a threshold cryptography or threshold signature would be to kind of distribute the trust among parties. So this is actually very similar to multisig that is either existing natively in some blockchains or in others like Ethereum, you need to write some smart contract or some functionality to achieve it. But this is what you try to get. So you can actually encode any access structure that you want, both in multisig and also in threshold signatures. However, using threshold signatures, you can hide the access structure. So the output, one of the requirements of the threshold signature is that the verification would be the same, right? So when you verify a multisig, you basically need to verify each signature separately. So it has some implications around the size of the transaction and also about the fees that you need to pay for it because it takes more space. But also there is this privacy issue that you can actually expose the access structure. In MPC, you require that the verification protocol would stay the same. So for an outside observer looking at the blockchain, a verifier, a miner, whatever, the signature should look the same. So no matter the access structure, it can be 500 signers that are somehow connected with some, let's say, AND gates, OR gates, and all sorts of like, imagine a circuit. Eventually, you'd get a single signature, which is the same size as a single signer signature.
That's the point of failure, is that there is sort of a traceability aspect.
I would say it depends on the use case. For some, if you have a really big access structure, so the fees might be something you cannot handle. So you'd want to have fees of a single transaction. But yes, it might also the size might be a factor, and also the privacy. So it really depends. Now, I want to connect it a bit to the research community and what was going on in academia. So a few people envisioned, Stephen Goldfelder, they saw a way that threshold cryptography can be used in a wallet, but the protocols of doing it, since in Bitcoin we use a protocol named ECDSA, which stands for Elliptical Digital Signature Algorithm. So the way of doing threshold ECDSA was not very efficient. So it was imagined, but never done in practice. And what happened is that during the same time that I started my company, there was a large body of researchers that tried to push this point. And because of the Bitcoin use case, found very clever ways and tricks on how to make this threshold ECDSA super efficient. Now, it's still very far from the efficiency you get from a single signer. First of all, you have to have communication. Like with all threshold cryptography, I mean, there's some state of the art now that try to minimize the communication, but usually with MPC, you need to exchange information. So there's the communication aspect here and also the computation. So you do need to involve some complex computation, and also from security-wise, there are some security assumptions that are not native in the blockchain, which is just the regular public key elliptical assumptions that you need to incorporate. Still, those protocols kept improving over the past 3 years until we have now really, really efficient ways of doing this threshold ECDSA.
I want to go back for a moment because I just want to redefine. You sort of made the distinction between the multisig and the MPC, and the threshold cryptography being a subset of MPC. Basically, you were saying that they're like with threshold cryptography, all inputs are the same size or are identical in a way. Can you just clarify what you mean by that?
I can clarify it by explaining about if we just look at signatures. So a signature is actually 3 different algorithms. One is a key generation, one is signing, and one is verification. So when you go to the threshold variant of it, so you have to find a way to do a distributed key generation or a DKG. The signing is also distributed, so you can call it distributed signing or threshold signing. verification must be the same as in the single signer case. So what it requires you is that the output of the signing, the signature algorithm, should look the same as in the single signer case. So it means that you take all the information from all of those, this might be, I don't know what size access structure, and you need to compress it into a single signature. So you do all these kind of mechanics inside the digital signature, but the output should look or should be of the same size as in a regular digital signature algorithm.
Got it.
However, in multisig, you basically concatenate different signatures, so it goes linearly with the number of signers.
I see. So you end up with do you actually add them? Is that kind of what you mean by that? You're kind of like putting one after another to make this like master signature?
Yeah.
Got it. Cool. That's been a helpful distinction, actually. Yeah. I've always been a little bit curious as to why multisigs weren't considered MPCs or vice versa, but it was cool.
Mm.
With this new kind of threshold cryptography, you've mentioned some of the pros or the benefits of it, but has it also opened up any problems?
Yes. So behind what I mentioned, that you do need to assume some security assumptions, depends on the protocol. So it might be that you need to introduce some new assumptions into your system, which is not preferable. You also introduce overhead in computation. You also require communication. So on top of it, the protocols themselves are extremely complex to write. Like I can say now with 100% confidence that it doesn't matter who tried to implement threshold ECDSA, they failed, including ourselves. Like you have to fail. This is one of the reasons why we are so happy to have this kind of ecosystem around it, because it got to be battled. This is the only way to gain trust. You have to battle test it over and over. You have to get new sets of eyes to look at it. You have to improve it constantly. Otherwise, you fail. This is one of the reasons, for example, Binance implemented a threshold signature library. And we found several issues that are in the algorithm itself, in the way they implemented cryptography that can be severe. Now, it's interesting because it opens up all kinds of new attack vectors because, we can go into specific examples of what it looks like to actually maintain this kind of, or to run threshold signatures. But the end result is that, for example, now we are also maintaining Binance library because we kind of see value in try to standardize it, try to make it as simple as possible, try to make it so their library is Go library, our library is Rust library. We want to make them interoperable, we want to make them with similar API. We see a lot of confusion around it, so it's really hard. Also, just to interact with those libraries requires some level of experience or knowledge of cryptography, just to talk with it, to use the API of those libraries. So, for example, in our case, in the Zengo libraries, we built a stack on top of it. So we have another library just to wrap the threshold signature library to make it more human friendly, such that you'd avoid mistakes around this, round of communications and so on. And then we have another library on top of it, which is more application specific. Now, if you want it to have threshold validation scheme, or if you want to have a threshold wallet, so you need to have another library. And even on top of it, we had one more layer just to wrap it, so to make the API completely foolproof. Because this is the cost of it. It's extremely complex.
But that Binance bug that you mentioned, was the problem that they had implemented too early before something was battle tested?
Binance did a fantastic job. They created state-of-the-art library. They used the right people to consult them. They audited the library, the code. The bugs that we found, and it's in plural, it's bugs. And also, again, we found bugs in many other places, including ourselves. And by the way, our library is also audited. The auditors are not familiar all the way with this new technology. So it's sometimes an issue. But even doing all this great work, you still can find all these cracks that are really hard to catch. It's really hard, for example, to explain. One of the main reasons is that you need to find someone that is fusion between a software engineer, a network engineer, and the cryptographer. And usually those guys do not meet. So it's
when they do, it's rare, I guess.
Yes. So it's hard to completely eliminate bugs. The only way to do it is iteratively by any other thing, like any other software. You have to keep battle testing it and like have experts look at it and contribute to it. It's the only way.
Yeah, I think it's worth highlighting that the only thing that improves it is time, right? I mean, even in OpenSSL that had been around for 20 years, there were severe bugs that were found. And so it's sort of, you can't ever expect anything to be perfect. And I think that's why it's great to have a community and a group and like a number of eyes who are actually looking at it from different vantage points, using it in production in different settings. And that's the only way you actually find stuff.
Yeah.
Can you give a bit more detail about the actual bugs, though? Maybe that helps us also to understand, like, what does a bug in threshold cryptography mean in the real world? Like, why would that be bad?
Okay, sure. So let me explain about the simplest bug that we found. So for this, I need to introduce another threshold protocol, which is secret resharing. So the goal of this protocol is it's extremely important. It's mostly when you do threshold cryptography in production, it's almost a must-have. So what you need to do is that an attacker, let's say that you thresholdize, this is the name that I use, you thresholdize your scheme, your cryptography. So now instead of one party, you have n parties, each one holds some secret. And you want to avoid a situation where an attacker gets hold of T+1 such secrets. But a clever attacker would go and attack one by one. So let's say you spread your secret shares to different sites. The attacker would just go to one side by the other and until he get enough secret shares that he can reconstruct the secret. So to avoid it, you need to add this notion of change with time. So you need to take some time parameter and after this time, you want to refresh the keys. So you want to keep the same secret key that is never reconstructed, but it should be the same. But you do need to refresh the secret so that you overwrite your old secret. This is also the mechanism if you want to introduce new parties into your group. So if some parties stop responding, you want to introduce new one. So this is part of this mechanism. And it happens like, for example, in DRAND, where they produce this random beacon, they do it, and it also exists in threshold signatures.
The name you're using here is secret share? Is that what the term you're using?
Yeah, I say that for each party holds a secret share. I mean, it doesn't necessarily means that this is it, but in the case of signatures, usually this is the case. So what happens in the Binance code is that, so you need to do this protocol to reshare. So again, the goal is that you have the same secret. This is like invariant in the system, should be kept, but the secret shares of the secret should be reshuffled. Now, to do it, you need each party to communicate with the other party. So each party would take his own secret and would share it with the rest of the n-1 parties. Now, what will happen is that it's enough for an attacker to attack, let's say, one party. Actually, it can even work for a network attacker, but let's assume that an attacker attacks one party. Now, this attacker would send the right shares to some of the other parties and an incorrect secret share to other parties. Now, there is a mechanism for each party. This is because we need to protect against malicious adversaries. So there are mechanisms for each party to check each message that it received and to verify that it received the right message. So this is all good and fine, but what happens is that this attacker would send some good shares and some bad shares. Now, the ones that receive the bad shares would detect it and would abort the protocol, meaning that they would keep their old secret share. The ones that received the good shares would continue the protocol, eventually overwriting their existing secret shares. So you end up with two groups of secret shares that are not compatible with one another, because one done a deletion, which is irreversible. The other one has not done a deletion, right? So two observations here is that one, it's really easy to fix. So you need to add another round of communication, which is obviously what the implementer wanted to avoid. And in this round of communication, you do need to kind of say, so each party needs to say, so I got everything right, I got everything wrong. And based on it, they get to consensus of what they should do. Another thing is that a smart attacker that goes undetected doing it once can keep doing it, eventually getting to some kind of an extortion situation if it involves money. So it can get to a point where you don't have in your N parties group enough secret shares to reconstruct a full key, only if you use one of the secrets or a secret that the attacker knows. So it kind of deteriorates the attack back to a single signer. or something like this. And then the attacker can say, okay, you want my secret share, so only if you sign a transaction that gives me half of the amount locked in this account or something like this.
So if you look broadly at, when you, as you put it, thresholdize various schemes, is there a class of problem or a class of attack that seems to pop up? Or is it, bugs as in any crypto software? Or is it actually like, no, these things we need to be aware of, these things are new things that pop up that come as a result of that?
So I think that at some point it would be possible to classify those type of attacks. Right now, all those systems are very new and the process is very manual. So what happens when you thresholdize a scheme is that you take out all the big guns in cryptography. So immediately it means that you need to, again, move to some kind of distributed system and also you introduce commitments and zero knowledge and homomorphic encryption and whatever. Like you just throw it all in and out of this, there's a lot of pitfalls that might happen. So, there are known issues that you can start look for. So the recent blog post I published was about an issue I found in several libraries that are doing threshold signatures, but different than EDDSA or ED 25519. And then you have some dependency in the elliptic curve. So you need to work in a specific subgroup of the elliptic curve. But what's interesting is that when you combine these two things, one is communication and second is working in the prime order subgroup of the elliptic curve, there's all sorts of issues. Like each message that you receive, you now need to also check something about the elliptic curve point that you receive, for example. And these checks, sometimes we notice goes like they are missing. And then there are all sorts of implications on what you can do. And apparently these checks also should be part of when you do some basic Sigma, like zero knowledge protocol proofs as part of the MPC and so on. So I guess there are ways that you can cluster those, but right now, the process, at least from my point of view, is very manual.
Another thing that I thought about, as you put it, you pull out all the guns to sort of thresholdize something, but I wanted to take a step back even before that, which is, you talked earlier about Bitcoin and having threshold signatures there, which could lead to multisigs or whatever that doesn't require Bitcoin script and all sorts of things. And now we're moving into Schnorr and we need better efficiency there, etc. But what drives all of these things? What drives these changes? What drives having threshold signatures at all? So what are the use cases, or why do we want these things at some level? I imagine there's many different answers for different fields, but if we look at Bitcoin, for instance, what's the prime motivating factor? Earlier you said for the wallets, having a social recovery scheme is obviously a big thing, but it feels like there's a lot of research that goes into this. It has to be more than a social recovery scheme.
Yes. So it really depends on, it's a great question. And there are all sorts of applications for threshold cryptography. And if you want to do the cross between threshold cryptography and blockchain, you can think about several killer applications. So one is indeed this new model, which is on the one hand non-custodial, but still gives you this kind of ways to avoid single point of failure. Okay, so this is, for example, one thing that we use in our wallet, and this was our design principle was avoid single point of failure. And once you go into this realm of, so you don't have a private key anymore, so it means that the attacker must be at, let's say, 2 locations at the same time to reconstruct the full private key. But once you go into this realm of having the key distributed and never reconstructed, so you can think of all sorts of stuff to build on top of it. So you can basically do a lot of what you natively would have done in a blockchain, either in a smart contract or in script in Bitcoin. You can do it off chain, and then your footprint on the blockchain would be minimal. So one example is a work we've done a couple of years ago about atomic swaps. But instead of doing it using transactions on chain, what I'm doing is that I'm switching secret shares between different parties. So if I can distribute one secret and I can distribute another secret, now I can trade in my secret shares. And we came up with this gradual release method that allows you to, let's say, switch or replace trade bit by bit until you get to a point where one party learns the secret share of another party while the other party learns this party's secret share. Eventually, you get to a point where one party controls, have a full control of some key that the other party now lost control of. Let's say you also do resharing. So without going into much details, you can build all sorts of applications around this when you have this ecosystem of not single key, but distributed single key. There are other applications in the field, ones that were worth mentioning that are getting traction. So one is the proof of stake validation. So let's say that you have a blockchain and like you run some consensus and you can run it with 1,000 validators, but it's not much. Like an attacker would control most of them, so your network will go down. So what you can do, you can distribute each validator into another 1,000 signers or co-signers, such that they need to cooperate together. So you get this factor of increase in security when you do this. There are already existing libraries, and actually Polychain, for example, labs are doing it already. So it's also getting traction. And it goes on and on. Like, for example, one work that we are now doing is about taking the watchtower concept of Lightning Network and showing, when you look at it from a key management perspective, how you can extend it into N watchtowers that are connected between them in a certain way that gives you some security benefits.
Yeah, I hadn't heard about that, the key trading thing. That's also fascinating. I do generally like the non-custodial, but giving custodial levels of user experience to be an interesting problem space that requires a lot of this.
Is there any connection? This is sort of a side thing, but is threshold cryptography and VDFs related?
No, not really. I mean, there is one connection, which is a project we worked with Ethereum. It started with the Beacon chain, and Beacon chain, to make the randomness unbiased, you need VDF. And to make a VDF based on RSA groups, you need to generate an RSA group that no one knows the secret key to. So to do it, you use a threshold cryptography. So Ethereum founded a very nice project that we reviewed, and going to present this process in real world crypto that is doing a massive MPC for RSA keys.
Okay.
And then you can get the public RSA key without the secret key, and then you can use it in VDF, and then you can use it in the Beacon chain.
So it's at a different step in this process. It's not deep in the VDF. It's rather before. It's the prep for the VDF.
I mean, there are ways to do probably threshold VDF, but I don't think it was researched so far.
Okay.
But this would be another cryptographic primitive that you can thresholdize.
Interesting. Going back to Frederick's earlier question of like why you need this, or like how it actually is the perfect solution for certain things. Do you have any other examples of that?
So there probably isn't such thing as a perfect solution. Everything is composed of trade-offs. But I mean, we know that it's very popular with exchanges. There are, I mean, the largest exchanges today, crypto exchanges, are using it. So think about this kind of model where you have like the exchange generates a single key, and this is like the master key. But now the exchange is using some kind of a two-party scheme where one party belongs to one group of signers from the exchange, and the other signer can be one of another group from the exchange, right? So let's say that in order to enable to confirm a transaction from some cold wallet to hot wallet in the exchange, you need to have the agreement or the consent of two groups, and you need to have one out of each. So this is, I think, a common case that you see in exchanges. Like you see you need from certain amount, you need one exec from this group and one operator from this group, something like this. And then you can go on and on with the access structure. So it's really convenient to define this type of hierarchies and access structures that allows you to have more control over how you confirm cryptographically. Like it's not going to be just an API yes, no. You actually need to confirm it cryptographically, which makes it much more secure way to enable this kind of confirmations.
I know it's starting to pop up like on the same similar vein as exchanges starting to pop up with validators, as you said as well, where a validator doesn't want to run everything on one machine. If that machine gets compromised and the key gets stolen, they can get double signed or whatever. There's various ways to exploit that or attack people. So they start spreading it out on multiple machines or multiple people that need to do stuff to or take action to break the system.
Yeah.
Some of the work that you basically shared with us in prep for this episode was about crypto wills. Can you tell us a little bit about that work and how that actually relates to threshold cryptography, if that's the right solution for it?
Yes. So I would first start with a higher level presentation without even like diving into the problem of how to do a crypto will, which basically means that, like, I mean, the issue I think is self-explanatory, but in crypto, you do need to have some relative or someone, you want to have someone that would be able to take in a non-custodial way, of course, your funds after something happens to you. So, but before going into this, just I think it belongs to, and this is the connection to threshold cryptography, to a broader range of questions around whether I should use and at what applications or what problems should be answered with or should be solved with threshold cryptography. So there are a lot of protocols that we want to imagine are happening between two sides. And those protocols can be mostly easily solved if you say, so let's say, okay, I don't want to trust any one entity in the world, but let's say that I can allow myself to trust that I'm adding this something in the middle, let's say a server, but this server is distributed in the sense that everything is threshold crypto. So it means that I can rely on the fact that out of these n servers, at least T+1 would be able to help me with any operation I want. So this is another example of a problem like this is the stealth addresses. So this is a problem that raised by Vitalik that we picked up and try to solve with his help. On how, let me give you the concrete example. Let's say Edward Snowden opens an account, an Ethereum account, and publishes his address and says, look, I'm looking for donations. Now you want to donate to Edward Snowden, but you don't want it to get back to you. Like you don't want a transaction on chain showing that you actually send money to Snowden. So you need to find a way to send him money without having this on-chain footprint that shows that you sent to his address. So this is stealth address issue. And with crypto I find it a bit parallel that, again, there's, let's say, not going into the terminology that we introduced in the paper, but let's say you have a sender and a receiver, and the sender should send something to the receiver conditioned on several conditions. One of them is something should happen only in the future. Another thing is that the digital footprint should be non-existent or something, or some conditions on it. Before the funds can actually be collected by the receiver. Now, in both problems, if you introduce this threshold assumption and structure, then you can solve them relatively easy. One goal of these papers is to put this solution out there and say, like, this is, let's say, the ground truth. Like, we know that we can do it. Let's formalize it, whatever, it's possible. For those that it works for them, it's great. However, it gets much more interesting when you start to remove this man in the middle. So in the crypto will paper, I think one of the interesting solutions that we try to show is that, let's say I'm removing this man in the middle or this threshold assumption with multiple servers by a trusted execution environment like SGX, or even specifically Intel SGX. So when you put SGX in the middle, we didn't want to count on the fact that the SGX knows the time. And we didn't want to count on the fact that SGX is confidential. So it makes the problem much more interesting. So there's a spectrum of solutions that you can try to forward the problem before you go into the full case of completely just two parties, like it's a two-party protocol that now needs to be solved in a very expensive way.
I mean, it's a fascinating question and topic, the crypto wills. What happens to people's, I mean, in the most maybe basic way is like, say someone passes away or doesn't have, they're trying to bequeath their crypto to somebody else. How do they ensure that that is done and that the certain kind of rules are followed? So for example, like maybe they don't want to reveal what's in there before they pass away, or they don't want to reveal who else is being bequeathed or something like that. I mean, it sounds like such a huge problem, but what you're saying is you found kind of like a subset of tools that you could potentially use to solve for this.
Yes, I mean, the research structure as follows. So you have the trivial solution, which is inefficient or requires you to trust someone. You have the more complex solution that requires you to have this structure of servers, but then you also need to have this kind of assumptions. And then we go all the way up to the point where you can do it just with the two parties that are involved. And yes, like you said, the conditions of the problem are dictated to you. Like, you know that it should have privacy. Like, you cannot reveal the because before you actually die, or you need to reveal it only to the right person at the right time. So you have this all the conditions, and then you just try to find this tool set that can help you solve it under certain conditions. And eventually what I hope is that people would take this paper and would find the solution that fits them best and would use this or build on top of it, because there are a lot of future questions. Because like you said, it's a huge topic.
Yeah. It's an interesting, like, philosophical and technical problem, like, combined, where the easiest solution is you just trust your lawyer and be done with it. But then you can go further and further. But I mean, at the last point, then, as I think it through, last point of sort of needing real world data is, how do you detect when someone dies and, like, trigger the scheme?
Yeah, it's so this is, you first need to assume something about the liveness of the whatever entity it is. So the way that we decide to define it is by having this kind of digital footprint. So it can be defined in several ways, but eventually you need to predefine, like, or to have some contract with yourself on what services are you plan to be active on and at what cadence. So it can be a blockchain. It can also be, I don't know, log into Facebook or to Twitter, whatever. And if you are inactive in those services for some time, then your will is supposed to be accessible. So this is like a condition. But we definitely keep this as an open question, because there's probably, it's an oracle issue. It's a big issue.
Mm-hmm. Also, it changes so much over time. Like, you know, once upon a time, I had a MySpace account that I actually visited a lot, but I would hate to have my daily activity of that be in any way referenced, or actually my Facebook for that matter. But it's sort of like trying to make your digital life be your life. Like, if you're active in some digital way, then you're alive.
Yeah. It's probably the simplest way, probably, but yeah, I mean, the paper raises many questions, and this is one of the major ones.
How exactly, and I know you started to explain it before, but where exactly is the threshold cryptography in that construction that you kind of came up with, or in one of the constructions? Like, where does it live exactly?
It's you need to have it out of the blue, and it raises other questions, like how can you deploy threshold structure? So how can you actually do it in a way, like in real world, in production, in a way that would maintain this threshold assumption of separating completely I call them N servers. So I just assume that you have in the sky, for the sake of solving the problem, I just assume that you have in the sky, you are given from God N servers. They are completely separated. They can act maliciously, but you assume that they cannot collude. All of them, like up to a certain threshold, they can collude. And you have a protocol that you need to design and prove secure that allows you to solve the problem using this structure. But it's really a hard problem in real life. Like, how can you need to have separate softwares in different languages, and it should be like, you cannot have an admin that like goes from one machine to machine and put, because this admin is a single point of failure. So you broke the assumption. Mm-hmm. Or you cannot have your CEO have access to everything. So you have to find ways to actually do it. And it's funny because I think most of the industry are not actually solving this, like, deployment issues.
So we're almost out of time, and it's time to start wrapping up. But before we leave you, I would like to hear more about the MPC Alliance, because this is something that you're involved with together with a bunch of other companies, and sounds like an interesting endeavor. But what is it really?
Okay, so thank you for bringing this up. MPC Alliance, it's a non-profit organization based in Delaware that puts as a goal to push forward MPC adoption through market education. So in the MPC Alliance, we have, I think now around 40 members, 40 companies that are different size and shape. So it might be competitors, it might be large organizations, Alibaba, for example, might be smaller ones, startups like my own. And we are all working together and we have our own network, try to come up with both technical contributions and marketing contributions to the success of MPC technology. So, for example, in the technical aspect, I can say that we have a Wikipedia. So this is kind of a community project, a Wikipedia for MPC, which is starting to gain traction. Like people start to add articles and so on. But it's ongoing for quite some time. And this is something that was never done before. We also put a lot of effort into standardization aspects of MPC. And from the marketing aspect, so we host webinars, we participate in webinars, in events by companies, and we will start a podcast soon, and there are blog posts, and on and on and on. And yeah, that's it. I co-founded it together with other two companies, Unbound Tech, which Nigel is the co-founder of, and another co-founder is Yuda Lindel, which was my supervisor at the university. And also with CPO, which is a company based in Denmark, California. And three of us founded it. And now we are together with Dan from Cybernetica. We sit in the board, but it started just a year ago. So it's just very early.
It's cool. And it's great to hear that you're going to be creating more and more resources for people to engage with MPC work. Will there be sort of specific threshold cryptography within that, or would you just lump that together? Like, do you think you're going to have to create subgroups as it evolves?
Within the MPC Alliance?
Yeah.
Yeah, so so there are, I would say, two large use cases for MPC, big use case for MPC nowadays. One is around security, which focuses on threshold cryptography, and one is around privacy. So privacy, machine learning, and so on. This is like a huge use case run by many companies. And it's divided. I mean, the alliance is like 50-50. So I know because I talked with all of the companies, I have a good industry overview. We have around 50-50 from also blockchain and non-blockchain companies, since blockchain drives cryptography. And the use cases in blockchain are usually around the key management and around security. So we already have this kind of subcommittees that are focused on the different applications and pushes them in their own domains and industries.
Cool. So Omer, thank you so much for coming on the show and sharing all of this work. We're going to add a number of links in the show notes for anyone who wants to follow along. And where can people find you or engage with these groups?
It's easy to find. So Zengo.com. It's everything you need to know about the wallet. There's a page about Zengo X that connects to both the GitHub and the Telegram group. And from the Telegram group, you can hop to any other one of the smaller rooms on Telegram, and you can ping me on Telegram as well, or Twitter.
Well, thanks a lot, Omer, then.
Thank you.
Thank you very much. Yeah.
It's a pleasure.
And to our listeners, thanks for listening.
Thanks for listening.